This is video number 10 in our topics in quantum mechanics. In this video we want to discuss some of the properties of the position operator. And again, remind you that the playlist for all the videos, you can find the playlist at digital-university.org. Okay, in this video, like I say, we want to discuss the properties of the position operator. And again now, for the next 10 or 20 videos, we're going to be mainly working, or not mainly, we are going to be working in just one dimension on the x-axis. So after a while, once you sort of lay out a foundation, we'll work in 3 dimensions. But anytime now, if you don't hear us referring specifically, we are just working in one dimension and just strictly on the x-axis. And the symbol then for the position operator on the x-axis is usually just x with a hat over it. And the way it works is if it operates on a state ket vector, say psi, all it does is it multiplies psi by the coordinate x. Like this. Or as we discussed now in the previous video, number 9, one of the components of the state ket vector is the wave function of the particle. So the position operator, say with the wave function, we're writing it as a function of x because we're confining ourselves to the x-axis. That would just be equal to the coordinate of the wave function times the wave function. And exactly what this means we'll examine it in a minute. But first, and again, we're on the x-axis, so these are real numbers here now. They're not imaginary numbers or complex numbers. Before we explain exactly what this means and the consequences of this definition, let's first check and see, is the position operator Hermitian? As we defined in the previous videos, a necessary and sufficient condition for an operator to be Hermitian is this. That this be equal to a real number. And as we explained in video number 8, the inner product of functions is the integral of the complex conjugate of the function, this, times this, which is just x, times the function. The complex conjugate of the function times the function is the inner product. This whole expression is this, and we're on the x-axis. And again, since we're on the x-axis, we're not in complex space at all. This is a real number. And of course, when you multiply a function by its complex conjugate, that's a real number. This is a real number. We're integrating a real number, so we're going to get a real number. So this right here certainly then fits the definition of a Hermitian operator. Now, with that out of the way, before we try to explain this further, if the position operator indeed is Hermitian, then it should have eigenvalues and corresponding eigenfunctions. Now, here then, that would mean that x, and again, we're just on the x-axis here, so x is just some particular coordinate there on the x-axis. X times psi of x would have to equal lambda psi of x. where lambda is just some discrete number. Now, to see exactly what this means, because it is strange, let's just move this over to this side of the equation. So we have x minus lambda psi of x equals 0. Well, that would mean then that this has to be 0 everywhere except where x equals lambda. So, again, if that's our x-axis, and if we're at a certain value lambda, then the function can exist there and only there, so it would have to be a spike. That's the only kind of shape that the function could have. Now, what describes this kind of a function? That's 0 everywhere except for one particular point, and then it comes out to be a spike. And in most textbooks, it's at this juncture, if they haven't done it already, that they introduce the so-called Dirac delta function. And that's usually written like this. And that equals 0 or infinity. It equals 0 if x is not equal lambda, and it equals infinity when x equals lambda. And again, what kind of function looks like that? That's sort of what Dirac made up, was this basic definition here, which in turn then fulfills this properties. So what we're saying then is that for the position operator, this is the eigenfunction. Right here is that this fulfills this definition. Now, what are the eigenvalues? Well, the eigenvalues can be any number along here, along the x-axis. Any value of lambda would work. When we define the Dirac delta function, we don't say, well, lambda has to be between 5 and 13, or lambda can never be anything other than a whole integer. No, there's no restrictions put on it whatsoever. So, for the momentum operator, its eigenvalues are really continuous then. And its eigenfunctions are this strange function here. Now, remember that for Hermitian operators, that, as we discussed in the previous videos, when they operate on a certain ket vector, it just gives a discrete constant times that ket vector. Or if this was operating on, and again, not any ket vector, this would be an eigenfunction of this Hermitian operator. If there was a different eigenfunction, say alpha, we'll call this lambda beta, and then here it would have another different constant times, we'll say the eigenfunction alpha. The point is that these are a distinct constant, and usually, well, not usually, with Hermitian operators, it's always that this constant will be different from this constant. Well, here for the position operator, it's strange because its eigenvalues are not just any specific number. There's a whole continuous spectrum of eigenvalues that can satisfy this definition. And the other concern is, well, first, let's ask this question. If these are the eigenfunctions, are they orthogonal to each other? Well, let's just consider just multiplying these. Let's say, for example, we had delta x minus lambda 1, and then we had delta x minus lambda 2. Now, this would just simply look like, here say at lambda 1, we have a spike, and then for this one, say over here at lambda 2, we have a spike. Now if we just multiply these together, I would have this one, which has a spike at lambda 1, times this one, which is 0 everywhere. So I'd have 0 times this, so that would be 0. Then here when I have this one times this one, here we have a spike, but where I have the spike for this one is 0, so I'm multiplying this by 0. So if we're multiplying two different eigenfunctions together, and lambda 1 does not equal lambda 2, it comes out 0. So they do satisfy orthogonality requirements for the Hermitian operator. Does that mean then that we can make them into orthonormal functions? And again, in video number 8, we had an example of functions that were orthogonal and what we had to do to make them orthonormal. And what it means is that when we take the integral of two orthogonal functions, just say I and j, dx, it equals 0 or 1. Equals 1 when I does not equal j, equals 1 when I equals j. Well, what would be the integral of this? Well, now we have to go back and talk about the Dirac delta function a little bit. The way Dirac defined it is that, now if we just had incidentally just this, that would be 0 everywhere except for the origin when x equals 0, then we would get this spike. But if you try to integrate such a function, what do you get? And again, the way that Dirac had defined these is that the integral of this we can go anywhere from minus infinity to plus infinity, just equals 1. And then again, though that kind of conflicts with our everyday math experience, what kind of function has this spike at one particular point, and then when you integrate it, you get an area of 1. And there are some functions that approximate this. We don't have to get bogged down in all of that, but we can demonstrate it with a rather simple example. Suppose that we had a function like this, where here the width of it was, say, epsilon, and the height of it was 1 over epsilon. Then clearly its area is 1, and then as this gets smaller and smaller and smaller, 1 over epsilon gets bigger, bigger, and bigger, so we could sort of imagine that as the width here becomes 0, you would have a spike, and the area of that spike would be 1, just magnitude 1. And again, that's kind of fudging it, and to really justify it further than that requires really going into the real mathematical properties of these Dirac delta functions, and really they're not functions at all. It gets into theory of distributions to really justify these different properties. But for us, the take-home lesson is that this is the basic definition of the Dirac delta function. This is one of its characteristic properties, and that the Dirac delta functions are the eigenfunctions for the position operator, and for the position operator, its eigenvalues take on a whole continuous spectrum. But now, what would be the inner product of these? Remember that, as we discussed in video 8, that we have this. If it's orthonormal, that has to be 1 or 0. Well, if we're dealing with these eigenfunctions, the orthogonality properties hold up all right. We just demonstrated that. But now, here then, if we're going to comport to this definition, that would be like taking the integral of having this squared. And now the math gets even more or less logical. And in fact, if you look at most textbooks, they would tell you that this is not square integrable. And by square integrable, all we mean is that this is orthonormal. When they say square integrable, all they mean is that you have, when you're taking the inner product like this, it just simply is less than infinity. In other words, it doesn't blow up. And what range? Sometimes you see the definition going from minus infinity to plus infinity, or sometimes they'll just say just in a certain region from limits from a to b. Well, the point is that you're multiplying a function by its complex conjugate. Well, here we have x minus lambda. We're dealing with both real numbers, so you've got this, the Dirac delta function here. So you got this weird thing squared, taking the integral of that. Most books will just say, no, that is not a square integrable function. So that means then that these eigenfunctions for the position operator don't lie in Hilbert space. In Hilbert space is comprised of complex functions, but they have to have this characteristic. Or if they're eigenfunctions of a Hermitian operator, then they are orthogonal, and we also want to be able to normalize them so that it comes out equal to 1 when I does not equal j. And again, we had a demonstration of that, a specific demonstration of that in video 8. Well, the problem here is that when you start applying this definition to this strange definition here, you run into problems. And the way it's resolved is we have to explore a little bit more of the properties of these, and there's a way of getting around it. It's called Dirac normalization, and we will handle that in a future video. Right now, we just want to point out that for the position operator, these are the eigenfunctions of it. Its eigenvalues are continuous. These are orthogonal, but they are not square integrable, so we're running into a problem with these eigenfunctions for the position operator. And what we're going to do in the next video, we're going to examine the momentum operator and see what its eigenvalues and eigenfunctions are, and we're going to run into the same kind of problems that we're encountering here with the position operator, but there's a way to solve it for both of them through the Dirac normalization process, and that will take care of in the future videos. So come back, join us for those videos. We'll continue with our discussion, and we'll see then how exactly we can resolve this dilemma here where these eigenfunctions are not really square integrable, and therefore they're not a part of Hilbert space.